there, and welcome to How'd You Get That, where we solve all your math and physics problems. I'm David, and today we are taking position, velocity, and acceleration, mashing them together, and seeing how things work because of that. Today we are taking a look at the kinematic equations. You may recall that kinematics is the study of motion, and it has three major building blocks: position, velocity, and acceleration, as well as time. Whenever we build a kinematics problem, we're going to be using these three quantities in different ways. And as we study kinematics in a beginning physics course, we're going to make one more stipulation, that the acceleration, a, is constant. Now this might not seem like a big deal, but in our everyday lives, acceleration is rarely constant. However, when we're trying to solve generalized problems and going through these problem-solving techniques, the simpler is often the better. So in order to make these problems solvable, we set our acceleration equal to a constant value. And this also allows us to introduce four super useful equations, the kinematic equations. We're going to be deriving these equations here generally, but not terribly mathematically rigorously. But they all stem from the fact that acceleration is constant. I'm going to give acceleration a value. I'm going to call it a. And remember that the derivative of velocity is equal to acceleration, and therefore the integral of acceleration with respect to time is equal to the velocity. So to solve for the velocity of a system where the acceleration is constant, we simply take the integral of the acceleration function. But the integral of a constant function is just a linear function, so I can write this: v of t is equal to a times t plus c, where c is an extra constant that we need to add to the end of an indefinite integral. I'm going to rewrite that constant c as another constant, v sub 0, or v initial. And this is our first kinematic equation. The velocity at any point in time is equal to the initial velocity plus the acceleration times time. And since integration is so much fun, why don't we do it again to find the position? So the position of a particle with a constant acceleration is equal to the integral of the velocity function. So if I do that, the integral of a linear function is simply a quadratic function, and I get this: x of t is equal to the initial times t plus 1/2 a t squared plus c, where again c is that extra constant that we need to add to the end of an indefinite integral. The reason I get 1/2 at squared here is because of the power rule of integration. Replacing c with the initial position now, x sub 0, or x initial, I get this second kinematic equation. The position at any time is equal to the initial position plus the initial velocity times time plus 1/2 the acceleration times time squared. Now something to note about these. The t I'm using here is technically a delta t. Very often we set t initial equal to 0, which means that delta t is equal to final time, or the time that we're looking for in the specific problem. But sometimes we don't want to set our initial time equal to 0, and therefore delta t is going to be the appropriate quantity to use. So a more accurate way of formulating these equations would be like this. Okay, so our third kinematic equation comes from combining these two kinematic equations. I'm going to solve our first velocity function kinematic equation for delta t, and then I'm going to replace that into our second kinematic equation, which is the position kinematic equation. If I do that, and I'm going to solve for v final in this case, I get our third kinematic equation. V final squared is equal to v initial squared plus 2 times a times delta x. Now here in this case, delta x is important. It's the final position minus the initial position, not just the final position times 2 times acceleration. These three equations will get you through most of kinematics, but there is a fourth kinematic equation that is sometimes used, and it is this: delta x is equal to 1/2 v final plus v initial times time. Now how I get that is I take the velocity function, the first kinematic equation, solve for the acceleration, and then plug that value into the third kinematic equation, the v squared kinematic equation. When I do that, after some simplification, I arrive at this equation. Each of these equations has its own utility, and which one we want to use really depends on what we're given and what we want to solve for in a given problem. So for instance, if I know the time and the final and initial velocities and I want to find the acceleration, maybe I use the first equation because it doesn't involve position. The second equation involves position and initial velocity, acceleration, and time. So if I don't know and don't care anything about the final velocity, maybe I use the position function here, the second kinematic equation. The third kinematic equation, if I don't know anything about time and don't really care about solving for it, I could use that one because it doesn't involve time. And the fourth one, if I don't know anything about acceleration, but I do want to know some stuff about position, time, and velocity, I'll use that one. But know that each of these equations solves for the same system. I can use any one of these equations to solve for a particular system. It just depends on what I know and don't know about that system that is going to make my decision about which equation I'm going to use. These four equations are ones that we can use anytime that we have a constant acceleration. And they also expand to 2 dimensions and 3 dimensions as well. When we move on to 2-dimensional and 3-dimensional kinematics, we're going to see that it's going to be important to break up these kinematic equations into one set for every dimension. For instance, in 2 dimensions, the position function equation looks like this. We have an x equation. X final is equal to x initial plus v initial x times time plus 1/2 a in the x direction times time squared. And our position function in the y direction would be y final is equal to y initial plus v initial in the y direction times time plus 1/2 a in the y direction times time squared. You'll see I've written subscript x's and subscript y's all over the place here, and that's because each of these coefficients and terms represents something different. The only time when they do equal each other is when they're written the same. For instance, time. Time in each of these equations will be the same, assuming we're looking at the same moment in time. So often in 2 dimensions, we'll exploit this fact by taking the time that something occurs in the x direction and equating that to the time that something occurs in the y direction. We'll look at that in a later episode. But for now, to explore these equations, it's best just to try out an example. So in the next episode, we'll be taking a look at this problem. But in the meantime, why don't you try it out yourself? If I accelerate in my car from 0 to 100 kilometers per hour in 3 seconds, over what distance will I have passed to get to that speed? And if I slam on the brakes after having reached that speed, such that my acceleration is now -30 meters per second squared, how long does it take for me to stop? Try it out yourself, and I'll see ya in the solution.